Hi, in this video I will show you how to calculate inductance in 3D in COMSOL Multiphysics. I have prepared two examples which I'm going to cover them one by one. The first example is a rectangular loop with a wire that has circular cross-section, like the picture that you see. We have actually analytical formula for this scenario, and the analytical formula is given here. L1 and L2 are the sides of this rectangle. A is the radius of the wire. And also we have another term which is named Y here. This Y basically considered the skin effect. So at low frequency, the current flows everywhere across the cross section. In that case, the value of Y will be 1, which because this is minus to minus is plus, so the inductance value will be at its largest. And when the frequency goes to very high values, what happens is that the current flows on the surface, so we don't have any energy inside the wire, therefore the inductance will decrease. And here also we can see that at high frequencies, the value of Y tends to become 0. And because this is 0, we don't have any addition to the whole term. Therefore, the inductance value decreases a bit. Anyway, we have this analytical formula. Actually, this analytical formula is from Wikipedia page of inductance. At the end of this page, there is a table which inductance of very famous geometries are given. This is for the rectangle from round wire. Anyway, so first we are going to model this, and after that we are going to add a toroid around this wire and recalculate the inductance. Now for this first case, which is only a rectangular wire, I'm going to make a geometry of 200 millimeter and 100 millimeter. So these are the size of the rectangle. The wire radius is 2 millimeter and the conductivity of copper is given here. We will evaluate it at two frequencies, one 50 Hertz and one 50,000 Hertz. Now, if you do the evaluation, if you do the calculation, put it in this formula. At 50 kilohertz, it's 0.419 microhenry, and at 50 hertz, it's 0.439 microhenry. We are going to do the simulation and see how close our results will be to these numbers. Now, for the second case, when we add the toroid, if you want to evaluate this scenario analytically, we need to do a little bit of work. First, I explain that one, and then we see the simulation. Okay, so this is here. The scenario is that we have a current flowing through this loop, and then we have a toroid here, which, for example, has a high permeability, let's say 1,000 or more. We can redraw this instead of having, let me turn on the laser. Instead of having like this, I can say that the current comes here, I go a turn here and then come back like that. On all of these regions, I did not add any current because everywhere we have a counter direction of current, so this is actually does not exist. However, if we consider this scenario equal to this, we can change this into something that is easy to calculate, because here we have one loop in a toroid, and then the rest is basically something like this. So this scenario can be converted into these two. Even for the toroid, we can see that there is some air space here. We can also convert this one into two inductances basically. So instead of having one big loop, I can consider going here, come down, go up, go back. So this becomes one case and this becomes another case. So we can divide this one into two smaller cases. So at the end, what we have is that this scenario can be considered as addition of three circuitry. One of them is like this, one of them is like this, and one of them is like this. Now, if you want to calculate the inductances, we have to calculate the matrix of inductance. Let's say for these three cases, we have 3 by 3, and then the total inductance will be the addition of all elements. We have to consider the direction of currents. For example, in this case, the current goes downward, in this case goes upward. So these two are actually opposite direction of current. So the mutual inductance will be negative, and same for these cases. Like this case, if you have two inductors that have the same direction of current through the coil, considering how the coil is wrapped, then the inductance will be L1 plus L2 plus 2M. But if it is oppositely made, then we have to subtract the mutual inductance. Anyway, so this will be the analytical kind of consideration, but we want to make simplified, so let us ignore this inductance, this tiny one, so I don't consider this. And also this one, it's a very tiny space, so I consider just the total rectangle. So basically this will be addition of these two. And since mutual inductance between this case and this case is also very small, so we just add the rectangular inductance plus one turn around the toroid. So if I want to evaluate this one, actually it becomes something like this. Not 100% accurate, but let's accept this. For a toroid with n turn, we can easily solve it analytically and we get an equation like this for inductance. And if I put n equal to 1, then I can calculate the inductance for one turn. Now, of course, when n is 1, this formula would not be very accurate, let's say. This formula is true if the current really distribute along the whole toroid. But let's leave that for another video. In this case, we assume that the formula is 100% accurate even when n is 1. So these are the parameters that I'm going to use. The size of toroid is this A will be 10 millimeter, this B will be 20 millimeter, the height is 20 millimeter, they have one turn, and this gives us 2.77 microhenry. And if we add them together, as I explained, to have an approximate value for inductance, let's say we consider 50 kilohertz. For rectangle, we had 0.419 microhenry, and for this one turn toroid is 2.77. So we add them together is 3.89 microhenry. We will see whether we can get these values in COMSOL. Now I'm going to show you how to make inductance calculation in 3D COMSOL. First, we start with a simple rectangle. All right, so now let us start with COMSOL simulation. We create a new model, 3D. Go to ACDC, magnetic field, double click, select the to study. We can select the frequency domain. We can also add a stationary. Actually, having a stationary analysis is easier. So I also make another as a stationary in case I want to evaluate it, but we will focus on frequency domain. I'm going to draw the geometry. So select the size as millimeter. First, we create a work plane. Okay, so we create a rectangle. Width is 200, height is 100. That's a rectangle. We can add fillets. So at the corner, we create some curvature with 10. Yeah, let's give it 10. I'm going to put the terminal in the center. So create another rectangle. Width 20, height maybe 20. This is minus 10. This is 90. Come up to this point. We can make union, add them together. Remove the interior boundaries. So we have something like that. We can create another fillet. Maybe how much? 5. Yeah. We can now convert this geometry into curve. Okay, I can delete this part because we don't want that. All right, so now this is the rectangular path. So here I create a path, and then later I will create another circle, and basically we sweep the circle along this path. Now, if you want to analyze the inductance in 3D, we need to define a coil, and for this coil we should say where the current enters and where the current goes out. Those boundaries where the current goes in and where the current goes out of the coil, it has to be faced toward an external boundary. Because we are going to put air around this coil, so that area will not be an external boundary, it will be internal boundaries. So I'm going to create another path here, and basically we are going to exclude that path from the solution, and therefore this little piece will be excluded from the magnetic field model, and so we get these surfaces becomes external surfaces. Okay, so what I'm going to do first, I'm going to create this circle to sweep this. So another work plane. Okay, so the work plane should be actually in ZX direction. Okay, so we come here, right click, create a circle, and maybe this should be here, I think, or maybe here. So the radius is 2 millimeter, the y is 110. Okay, so the circle is there. This plane has to move here. So because I created a fillet of 5, so I think this whole plane should be moved 5 unit maybe, or minus 5 unit. Yeah, okay, so now we have the cross section. Oh no, it should be minus 10. Should start from here. We have the cross section, we have the path, we can sweep this. Right click, sweep. We select this one, and then we have to select the path. We can also remove the input object, so we can sweep. Okay, this didn't work because we have to select reverse direction. So we have already created this 3D loop. As I said, we now have to create another external boundary here so that we can perform our simulation. So I'm going to replicate these two because we can use them. Here, let's say I don't need these things. I don't need these, delete. So if I create this one, but I don't want the height to be 10, and then maybe this minus 20, so this comes here. Delete this union, delete only these two, convert to curve, delete this part. Okay, so I have created that extra path, and this one is the same thing, the circle that we have created before. And now I'm going to sweep. This one here, I will select this path. Remove the internal object. So this is basically the other section. So we have created our rectangle. This is already very good. Now I'm going to add the air around it. So right click, create a sphere. Here, for example, a sphere should be y is 50, x is 100. Maybe radius, we put it 200. Okay, I create another sphere. You can select this one to be infinite domain, but in this case, I will not select it, just a little bit larger space. Okay, so we have created already our geometry. Now we have to assign material, right click on the material. So only the outer one and the inner sphere. So let's say mu is 1, sigma permittivity is 1. Sigma, even though conductivity of air is very, very small, you don't want to set it too small. Maybe set it 1 or even 10 in some cases. That helps the problem to be solved smoothly. And it does not affect the results. Okay, so this is material 1, and then now I can put material 2, which are basically these things. I can put them as coil, even though these parts will not be considered as coil. So mu, you can put 1, sigma is 5.8 e power 7, and permittivity. Let me delete these parts. I don't want to put them. They are not part of the solution, so it doesn't matter, but maybe I put them as air. But actually, it doesn't matter this part. You don't need to define. All right, so now we are done with assigning the material. We are going to make the coil. So in magnetic field, first of all, we are going to remove these parts from the magnetic field physics. We don't want to solve for this area. These are external parts. Now you right click, create a coil, select the coil. Okay. And then in the coil, we have to define where is the input, where is the output. click here, select the domain, and then hide this part. So this is going to be your input, and then right click here, select an output. This is going to be the output. So the current goes there and come back. Okay, so far so good. Bring everything back, select domain, maybe hide the two part. Okay, all right. The next part that is very important is the mesh. So we are going to add the mesh. Right click on the mesh, create a sweep, and select all these areas basically. But before that, we have to change this one to domain, and then we can select all of them. You can directly create it. You see that the mesh will be very bad. So we can add actually a size. So in this case, I can change the size so you can increase it, or custom. So let's say 1 millimeter. This creates such a structure. This one actually is very good mesh, but let's say this we were lucky, so that we just selected a number that it created very nice mesh. What you can do is that you can right click and create distribution, move this distribution above the size. And for this one, let's say these parts, they have more or less same length. I select them, and I'm going to add 5 units. So you can see that it will be 5 on them. So if we change them, let's say to 30, 20, we will have more. Let's put 50. Yeah, this is how it divides these parts. And then you can add more distribution. So each sections that are more or less similar, you can select them in one group of the distributions, and you can mesh them properly. So this one, let's say if you select 5 units, then it becomes like this. If you select 10 units, then it meshes like that. That is also good. Another distribution, let's say I select this one, and this, let's say I give 100, something like that, or maybe 110, 120. Yeah, so we have this control, and for the rest of it, so you can select another distribution here, and let's say we say these one are selected, and we want 20 or 10. No, you notice that these parts are small, so we have to actually divide them into different sections. So these 4 should go in one distribution, this one should go in another distribution. So I delete this and maybe this one. Yeah, and now in this case, by default, the other one is also created, but I'm going to make it myself. So these 2, and then we create 10. 10 will be more, so we create 5. So basically for each section, you can select the distribution. This is very critical. And now we are going to create mesh for the other domain. So domain, we bring back the big spheres, remove the first one. I select here, and this one we can select also size. Let's say fine, or maybe a bit better, finer. And then finally the last part, the remaining, the other sphere, we can also create mesh for that. Okay, so far we have created a mesh, but now before we continue, we should evaluate this mesh. So right click on the mesh, first see the statistic. Okay, so in the statistic, I see that I have 265,000 mesh, and the quality of mesh, minimum quality of mesh is very important. In this case, it's 0.12. It's okay. If this one goes to be, let's say 0.001, 0.002, is very low value, then you want to change your mesh, because otherwise it will create problem and COMSOL will not converge in many cases. We can actually check the quality of the mesh. So I right click, you click plot, and then basically you have this one. You can select different type of elements. So for example, if you see this one, this is only those beautiful meshes that we have created. And if we select pyramids, then we see how this one is connected to the next space. So this is, for example, a bit low, but in general, for the mesh that we created is okay. Now, sometimes this one will not be very okay. You have a lot of red with very low mesh quality. What should we do? It's very simple. You notice this one, they have some orange one. For example, I go back and this one, you see that there are some orange one here. We go back to distribution that we have created. So let me hide this. So this distribution was for these sections. So I'm going to change this, maybe put it 60. And I bring everything back so you mesh it. Then we can check the quality again if it has improved or not. So you repeat this process several times until the quality is as you want. Yeah, then you can proceed. So of course, in this case from original, it was very good. So now the quality even improves 0.20. And we can see the meshes right now, pyramid. So you notice that this part, which we have changed the distribution, now becomes mostly green. This part, we could also improve it and make the mesh for this region also better. But this is basically the trick. Now we have done the mesh. We can continue to run the simulation. We select the frequency. Let us start with 50 Hertz. To solve these type of problems, what you have to do is to right click on the study, add a geometry analysis. So you go to study steps, others, coil geometry analysis, and bring this front. And basically now we are going to solve this one. So when the simulation is running, have an eye on convergence plot. And if it keeps going down, that is good sign. If it starts to going up, then it most likely will not be able to converge and it will waste a huge amount of time. All right, so in this case, it solves the problem. What I suggest is that for this scenario, you right click on results and create a 2D plot. We are going to create another 2D plot for current density because we can see current density in the conductor. Okay, so the current density is uniform in the straight parts. That's understandable. Frequency is very low. When there is a bend, obviously this path is shorter, so the resistance is less. Current prefers to go on this direction. That is also very understandable. And okay, so we have the current density plot. You can come on derived value, right click, global evaluation. And then here you can select the coil parameter, for example, inductance. We're going to evaluate the inductance. So this gives us 4.47 times 10 power minus 7. And we have actually calculated this. What was the value we calculated? We calculated at low frequencies 4.39. So it's more or less similar to what we have here. It's a little bit different, of course. This is 4.47. This is 4.44. So a slight amount of deviation. But of course, we have also a kind of terminals here that adds a bit of length. So we accept the results. Now I'm going to change the frequency to 50 kilohertz and we see the results. All right, so the simulation is done. We can look at the current density. You notice that frequency is high, so current flows on the surface and obviously at the corners because it's shorter, the current flows even more on this side. That is understandable. We can calculate the inductance value. So we see that it's 4.26 and the value that we calculated by formula is 4.19. So there is a little bit of deviation, but we accept this one. All right, so this is it for the first example. In the second case, I'm going to add a toroid and basically we see how that toroid affects the total inductance value. So we come to work plane, we create another work plane and basically here we're going to add the toroid somewhere here. So we need a rectangle. The side width is let's say 10, height is 20. This is our toroid, and this should be 40. Okay, so this is the toroid that we have. I'm going to revolve it. Okay, maybe these things I should move them before these spheres so that I can. Okay, this is alright. So we have this one, and they are going to revolve it along this axis. So the axis is y, point is 1. That creates my toroid. Maybe we can also delete the internal boundary. So this is good. And then we create the sphere. So these are also good. In material, we create a new material. You have to hide this, hide this. We select this one. Maybe from magnetic field is this one. We should include it. And then in the material, we have permeability, let's say 1000, sigma, whatever you can put. I put it 10, let's say epsilon 1. Okay, so we have the toroid. And then in the mesh case, we should create another sweep for these. And we select domain, select this one. We can create size and also distribution. Yeah, let's see what it creates for us in normal case. So maybe we have to change this. This is what we have. Change that a bit. Distribution 20 maybe. 20 is a lot. So you have to play with it to create some very nice okay, so this is, let's say, the structure that I choose. And then we have the other meshes. So now first we evaluate how many meshes we have. We have 300, and the quality is also very good, 0.17. We can actually see that. So this is the mesh quality at this region is very good. This one is as before, but we could actually change this if we wanted, but it doesn't matter in this case. So this distribution is for that part, so we could maybe make this 150. I think that will improve the quality of that part. Okay, so if we look at this, you notice that this is very good. And the statistic again, this one is also really good. Mesh 330,000. The number of mesh, as I said, is very important. For example, my computer, this one has 32 gigabytes of RAM. I don't want to go more than a million or maybe 1.2 million mesh. Then it becomes very slow. So depending on the size of the RAM that you have, you should really control how many mesh you create. Otherwise, your simulation will be extremely slow. All right, so we have created this. I'm going to run the simulation, let's say for this case, and we see what we obtain. All right, so the simulation is done. We can look at current distribution. Okay, similar to before. We notice that for this side of the wire, which we don't have a toroid, here we have more current distribution. However, for this case, they are more or less equal. Anyway, we evaluate the inductance. It's 3.17 microhenry, and what we calculated here was 3.89, so very similar. This is basically how you can perform 3D inductance calculation in COMSOL. Extremely important is how you set up the mesh and use sweep to create the mesh, and also add distribution to properly create the mesh, basically. Okay, see you next time. Bye!